Alright, hello class. In this video, we're going to be talking about section 2.6, which is about the Cauchy criterion. Alright, so one of our biggest problems in analysis so far is our definition of convergence of a sequence actually requires that we know what the sequence converges to. Alright, so when we look at the definition of convergence, right, we say that A sub n converges to A if for all epsilon greater than 0 there exists a capital N in the naturals such that the distance between A sub n and A is less than epsilon for all little n greater than or equal to capital N. All right, and this, we need to know what the limit is to use this definition. The problem with this is that we don't always know what a sequence is converging to. In fact, I'd say most likely, given a sequence out in the wild, we won't actually know what it's converging to. So the problem is that we have to know what A is to use this definition. Okay. Now, we did find a way around that when we found the monotone convergence theorem. With the monotone convergence theorem, we were actually able to show that a sequence was converging if we could just show it was monotone and bounded. And then we had a trick to actually find what the limit would be from that. Okay. But what if the sequence is not monotone? Okay, what if, if it's not bounded, then it's not going to be convergent anyway, but is there a way that we can determine, so here's the question, is there a way we can determine whether a sequence converges without knowing the limit? And the answer is, of course, yes, but we need a new definition. Okay, and this is where Cauchy-ness comes from, right? Cauchy was a mathematician from back in the day. I think in the book it talks about him a little bit. Anyway, let me show you what the definition of Cauchy is. Okay, so a sequence AN is Cauchy, and it is pronounced Cauchy, even though it looks like Cauchy. It's Cauchy like Yoshi. If and only if for any epsilon greater than 0 there exists an capital N in the naturals such that, so far it seems like the same definition, but here's the difference. Okay, so if there exists a capital N such that AN minus AM, absolute value, is less than epsilon for any N and M greater than or equal to capital N. Okay. What this is essentially saying is that instead of saying that the distance between the terms of the sequence and its limit are getting smaller and smaller, Cauchy-ness is saying that the terms themselves past a certain point are getting closer and closer. So that's where the difference comes from. right? So with convergence, it's saying that the distance between the terms a sub n and the limit, which would be a, are getting closer and closer together. Or the distance between them is getting, so I should change that. So the distance between the terms and the limit a is getting closer or I should say getting smaller and smaller. However, Cauchy is saying that the distance between the terms themselves is getting smaller and smaller. Now, here's the question. Is there really a difference between these two concepts? And essentially, the answer to that question is actually very complicated. It really depends on what world you're living in. But in the real line, okay, convergence is pretty much equivalent to being Cauchy, right? A Cauchy sequence converges, a convergent sequence is Cauchy. This is only true in complete spaces. Now, we know that R is complete based on our axiom of completeness. Okay, but this is another thing we could actually use as our axiom to start analysis with, is the axiom that every Cauchy sequence is a convergent sequence and vice versa. Okay. All right, before we start proving some of these things, I want to show sort of a graph of what we're talking about. So if a sequence is Cauchy, what ends up happening is, early on it might be acting sort of wild, but eventually the idea is that it settles down. Okay, so if I pick a certain epsilon, so let's say here is my epsilon. It's a kind of smallish epsilon, and I just chose it around here. And this may be a sub n. Now, every other term past this n, okay, the distance between each one of these terms is less than epsilon. Okay, so that's what we mean when we're talking about Cauchiness, is that any epsilon I choose, if the sequence is Cauchy, then eventually all the terms will be within that epsilon tolerance of each other. Okay, and we can continue, if the sequence is Cauchy, we can continue to reduce that epsilon tolerance smaller and smaller, and then every term past a certain point has to be within that little epsilon ribbon, you can think of it. And as we make that ribbon smaller and smaller, if the sequence is Cauchy, we can always find a point where every term past that point will be in that little epsilon ribbon. Okay, another way you can think of it is on a number line. Oh, that'll work. And let's say our sequence is going along, and I know it's Cauchy. So what that means is eventually, whatever epsilon I choose, as small as that epsilon gets, eventually I know that if the sequence is Cauchy, that all of the terms of the sequence have to live in one of these epsilon neighborhoods, and at least every term past that particular n. So because we can keep making that epsilon smaller and smaller and smaller, it makes sense, hopefully, that, well, a couple things. One, the only way you could actually draw this, since sequences have an infinite number of terms, is if it actually does converge to something. The second thing is, well, also, it hopefully is pretty clear that it has to be bounded. Okay, which if it converges, that means it's bounded. Okay. All right. Now, again, the advantage of a sequence being Cauchy is that we can prove that a sequence is Cauchy without knowing what its limit is. Okay. Whereas if we only had the definition of convergence, we would need to know what the limit is ahead of time. Okay, so let's prove this important theorem. All right, and this is the Cauchy criterion here. It's theorem 2.6.4. And it essentially states that a sequence converges if and only if the sequence is Cauchy. Okay, so and this is what allows us to choose either when we're looking at a sequence. So if we know what the limit, or we think we know what the limit will be of a certain sequence, well, we can just use the definition of convergence. If we don't know what the limit might be, but we still need to know if the sequence converges, we can just instead prove that it's Cauchy, because all we need for Cauchiness is that the terms themselves, you get closer and closer together. All right, the distance between them gets smaller and smaller. Okay, so to prove this theorem, we actually need a particular lemma. Let me write it here. And I think in the book, let me look it up here. In the book, it's lemma 2.6.3. which is that Cauchy sequences are bounded. All right, and how we prove this lemma, we basically prove it in much the same way as we did for the sequence, for the convergent sequences are bounded. Okay, so the proof is done in a very similar manner. To proving that convergent sequences are bounded. Okay, so what we're going to do is basically we'll start by saying that since, or actually let me name my sequence here. So let a sub n be a Cauchy sequence. Okay. So there exists a capital N in the naturals such that the distance between AN and AM is less than 1 for all N and M greater than or equal to this capital N. All right, so this is basically just applying the definition of Cauchiness here. Because remember, if it's Cauchy, that means for any epsilon I choose, I can find a goalpost where everything past that goalpost is less than that epsilon, or the distance between the two is less than that epsilon. So it's true for 1. So what we're essentially doing here is we're choosing epsilon equal to 1, and since we can find a capital N for any epsilon, we can certainly find one for epsilon equal to 1. Okay, and then we'll play with this like we did last time. Okay, but before I do that real fast, if this is true for all N and M greater than capital N, then what I can do is say this instead, that AN minus A capital N is less than 1 for all little n greater than or equal to big N. Okay? All right, so this gives us that AN minus A capital N is trapped between -1 and 1. Which will give us, I'm going to move this over, this gives us that AN is less than A capital N plus 1. Okay, and then this, I don't know if AN or A capital N or either of these, I don't know if they're positive or negative, so I'm just going to say that this is less than or equal to the absolute value of A capital N plus 1. And this is true for N, little n greater than capital N. Okay, from here we can say that the absolute value of AN is going to be less than the absolute value of A capital N plus 1. And just like we did before, and let me put that for all little n greater than or equal to capital N, then what we do, like we did before, is we basically take the maximum of all the previous terms and this particular term. So, letting capital M be the maximum of A1, A2, A3 on up to A sub n minus 1, and then A sub capital N plus 1, we'll have that the absolute value of A sub n is less than or equal to capital M for all n in the naturals. Okay, so I know I breezed through this one a little faster than I did maybe last time, but it's essentially the same proof as we did before with the convergent sequence, just very, very slightly different. Okay, and we're using the A capital N instead of the limit A. Okay, but it's the very similar idea. All right, so now that we've gotten through that limit, or lemma, sorry, we can go about proving theorem 2.6.4. Okay, so basically a sequence converges if and only if the sequence is Cauchy. Okay, so we have two directions to look at when we prove this. Okay, we have this direction, the forward direction, that basically is convergence implies Cauchy. And then we have the other direction, which is that Cauchy implies convergence. Okay, we have to prove both directions since we're trying to get an if and only if here. Okay, and one of these is fairly easier to deal with than the other one, but they're similar. They're both going to use the triangle inequality essentially. So let's start with the proof of this first direction. All right, so I'm going to let A sub n be a convergent sequence. Okay, and we wish to show that an is Cauchy. Okay, so what we're going to start with is suppose, well, let's do this. Let's let epsilon be greater than 0. So that's always the way we would want to start these. And suppose that an converges to A. Okay, I'm just picking A as my limit. Then there exists a capital N in the naturals, okay, such that an minus A absolute value is less than, I'm going to leave this blank for right now. I don't know exactly what I need yet. Okay, but I'm going to go back and fill this up. So I'm just going to call this square for right now. I'm going to fill this in later. And this is going to be true for all n greater than or equal to capital N. So in other words, I know I can get this distance between an and A as small as I would ever want. So what I want to do is, I know I probably want something in terms of epsilon, but I'm not quite sure yet. All right, so we wish to show that this sequence is Cauchy. So we want to show that the ANs are Cauchy. In other words, we want to show that the distance between AN and AM are less than epsilon. Okay, so that's what I'm going to start with. I'm going to start with this. So for n and m greater than or equal to capital N, we'll have that an minus am absolute value. So I'm going to try and show that this is less than epsilon. So I'm going to try to get this less than epsilon. Okay, so how I'm going to do that is I'm going to then take it back to what we have here. So I know that an minus a absolute value is less than whatever I want it to be, however small I want it to be. So I'm going to do our little trick and add and subtract a, right? So this will be an minus a plus a minus a sub m. And now we can use the triangle inequality to get an minus a here. And this is a minus am absolute value, but remember, distances are symmetric, and so that's what I'm doing here. So I'll say distances are symmetric. All right. Now, okay. Now this is basically what we have up here, because with this distance, we can get as small as we want for all n greater than or equal to capital N. So we definitely have that here, but note our little m is greater than or equal to our capital M as well. So we can get both of these less than whatever this particular value is. All right, and now that I'm here and I know that I have two of them, I'm going to choose epsilon over 2, because epsilon over 2, they'll add up to give us exactly epsilon, and that's exactly what we wanted here. Okay, so maybe I should also say, therefore, the sequence AN is Cauchy. Okay, so when you read these proofs in the book or in a paper or whatever, no one's pulling this epsilon junk just right out of their brain, right out of nowhere. It does come from somewhere. It comes from, it needs to sum up to be epsilon at the end. Or that's what we try to get it to be. Okay, so eventually we get down to here and realize, oh, okay, if I did epsilon half plus epsilon half, they'd come up to be epsilon. Of course, since we can get this as small as we want, it doesn't have to be epsilon over 2. We could have done like epsilon over 100 and gotten the same result. It just would have been epsilon over 100 plus epsilon over 100, which would have been less than, here, I'll do it over here in blue. You'd get less than epsilon over 100 plus epsilon over 100, which would be epsilon over 50, which would still be strictly less than epsilon, and that would still get you what you want. Okay, so it doesn't necessarily have to be exact. This is just what's sort of considered good form. But honestly, it's not that crucial. Okay, you just need to make sure it ends up being less than epsilon at the end. Okay. Now let's look at the other direction. Okay, this other direction is actually a bit trickier. So we're going to start by letting this sequence be Cauchy, and we want to show that it converges. And here's where we run into the problem. The problem is, to show that something converges, we need to know its limit. Right? We need to know the limit to do that. Okay, so what can we do? Well, we don't necessarily have to exactly know the limit. We could do some work and get a candidate for the limit and then show that it converges. So here's where, and this is definitely the way trickier direction, because what we're going to do is we're going to use our lemma that we just proved for this theorem, the bounded one, and then we're going to use the Bolzano-Weierstrass theorem, and this is where, as I mentioned in that lecture, a very, very important theorem in analysis, and part of the reason for that is because it helps us prove this direction of this theorem. And remember, any theorem that has a name is pretty important, and this one also is named after Cauchy. So here's what we're going to do. We're going to say that AN is Cauchy, and so by lemma, it was 2.6.3, AN is bounded. Okay. Now, since AN is bounded by the Bolzano-Weierstrass theorem, okay, AN has a convergent subsequence. Okay, so suppose A sub nk is this convergent subsequence. And suppose this A sub nk converges to, let's say, A. All right, so we're going to utilize two things now. All right, so we've got pretty much all the pieces we need here. So I'm going to let epsilon be greater than 0. Okay, now since the sequence AN is Cauchy, there exists a capital N in the naturals such that, AN minus A sub m absolute value is less than, and I'm going to do the same thing I did before. I don't really know what I want it less than. I'll fill that in later, but I can get it as small as I want for n and m greater than or equal to capital N. Also, right, and actually I'm just going to call this n sub 1 just to be careful. So also, since A sub nk, the subsequence, converges to A, right, there exists a capital N sub 2, let's say, in the naturals, such that A sub nk minus A is strictly less than, and I'm going to say it's going to be epsilon something, for, let's say, n sub k greater than or equal to n sub 2. All right. Now let capital N be the maximum of N1 and N2. All right, then I want to fix at little n sub k greater than or equal to this capital N. So I'm fixing this. In the book, they make the subscript capital, which is kind of hard to see, actually. So just bear with me here. At this point onward, I'm fixing this n sub k greater than or equal to this capital N that we just established. Okay, so then for little n greater than or equal to this capital N, we have the following. Now here's what I want to show is less than epsilon. I want to show that this thing, right, that this is less than epsilon, because that is basically showing that AN converges to A. Okay, so remember how I said we needed a limit or a candidate for the limit, I'm using the fact that our sequence has a convergent subsequence, and I'm going to use the limit of that subsequence to be the limit of the whole sequence. Okay, so from here, I'm going to do the same exact trick we did in the previous part, except I'm going to use this fixed n sub k. So the absolute value of an minus a is going to be less or equal to, the absolute value of an minus a n sub k plus a n k minus a, which will be less than or equal to a n minus a n sub k plus a n sub k minus a. Now, this guy, okay, is going to be less than whatever I want it to be here. So this will be strictly less than this first one here. So that's, I'll call this star. And this one is going to be strictly less than whatever we put here. So I'll call that heart. Okay, and I want these two less than epsilon, so I'm going to do the same thing again. I'm going to say that this is less than epsilon over 2, this is less than epsilon over 2, and fill these in here to get that they're both equal to, well, together they are equal to epsilon. So we have that the absolute value of an minus a is strictly less than epsilon, implying that an converges to a. All right, and this completes the proof. All right, so I know this has been a pretty brain-melty lecture, but I did want to close this section with a bit of a discussion on what it is we're actually saying here. And this is one of the final ways that we can really define the real numbers. Okay, and that's that Cauchy is equivalent to convergence. All right, this is a property of being a complete space. Okay, now you might think that this is always true, and in a sense it is. What we're talking about is not that a Cauchy sequence can possibly diverge. Okay, it's more that your Cauchy sequence, if you're in a space, so let me put it this way. Cauchy sequences sort of will converge by definition, okay, just by their nature. However, if your space that you're working in is not complete, then your sequence may converge to something outside of your space. Okay, so you know, it's the idea of them converging, getting closer and closer together, closer and closer to something. Well, surely they're converging to something because the terms are all getting closer and closer together. However, if your space is not complete, in other words, if it has holes, then it's possible your Cauchy sequence is actually converging to one of those holes. So to give you an example of that, here's a sequence from the book. All right, so here's the sequence. It's x sub n plus 1 is equal to 1/2 times xn plus 2 over xn, and x1 is equal to 2. Now, I'm not going to take the time to prove some of the nuances here. You can prove that x sub n is monotone and bounded, and therefore converges by the monotone convergence theorem. Okay. And is therefore Cauchy by the Cauchiness criterion, the Cauchy criterion, right? So this is a Cauchy sequence, right? So this is a Cauchy sequence. Now imagine if our entire space was the rationals, then notice that the entire sequence xn is in Q, right? Because x1 is 2, then x2 is going to be 1/2 times 2 plus 2 over 2, so that's going to be 3/2. That's also in Q. And x3 will be 1/2 times, that will be 3/2 plus 2 over 3/2. We could, crank that out, but that's also in Q. And each subsequent x is going to be in Q. So xn will be in Q. Since Q is closed under all of the operations that we're doing here, right? We're doing a division and multiplication and addition and all of the operations that we would want it to be. So it's closed under addition and subtraction and multiplication and division. However, when finding the limit, right? So if we say that xn converges to x, we can do that trick we did before where we put in the x's here. We would get x is equal to 1/2 times x plus 2 over x. All right, and then we can solve this equation to find what x is actually equal to, what this sequence is actually equal to. So I'm going to start by multiplying everything by 2. And then I'll multiply everything by x because I want to get rid of this denominator here. So multiply everything by x, we'll get 2x squared is equal to x squared plus 2. And then if I move this x squared over, of course we get x squared is equal to 2. So x is equal to plus or minus the square root of 2. And you could just take some time to, it would require a lot of induction proofs to actually prove all these things I'm saying here. I don't want to take the time to do that because I'm trying to show something very specific here, but these are all going to be positive just based on the way that this is working. So therefore, xn converges to the square root of 2. Okay, so xn is in Q for all n in the naturals. However, its limit, the limit of xn, which is x, is not in Q. Okay, this is what I mean when I say that a Cauchy sequence converges. And I don't know why I put an E on that. Okay, so to sort of bring it full circle to one of the first things we were talking about in this class, right? We know that the naturals are closed. So let's do our closed thing. The naturals are closed under addition, not subtraction, but they should be closed under multiplication as well. The integers are going to be closed under addition, subtraction, and multiplication, but not division. Right? The rationals are closed under addition, subtraction, multiplication, and division. And then here is what we get with the reals, and this is what makes R complete. R is closed under addition and subtraction, multiplication and division, and limits. That's the whole punchline of this, is that R is closed under limits. That means if a sequence is in the reals and converges, then its limit must also be in R. Okay? This is what we mean by complete, i.e., there are no holes, there are no places where we could have a sequence converge to something that's not there. Okay? Now, here's the next important part. We've had a lot of trouble trying to jump from Q to R. Right? That jump has been kind of difficult. Right? This is a difficult jump. Well, here's a question. Is R just Q union all of the limits of all the sequences in Q? Okay, is that how we can make that jump? Right? Can I just take, in other words, to jump from Q to R, can I just add in the limits of all the sequences? And essentially, yes. It has taken us a long time to get here. And in the next chapter, actually, we're going to answer this question formally. But yes, that's the answer. The answer is, when we jump from Q to R, what we're doing is we are taking all of the limits of every sequence in Q and putting it in, and that gives us all the real numbers. It fills in all the holes. Okay, so that's sort of a spoiler for what we will be looking at in the next chapter. And I will leave you all there, and I will talk to you all in the next one. Cheers.